Hi everyone, we are back and we are on problem number 2, my favorite problem, polymers, XRD, lots of cool things to do about polymers. So let's take a look at the polymers here. So I have polyethylene, I have some of these other polymers. So I know that polymers 1, 2, and 4 are semicrystalline, polymer 3 is amorphous. I'm interested in working with these polymers in a mystery solvent and find that polymers in 1 and 3 expand, 2 collapses, and 4 is unperturbed from the melt state. So describe the relative strength of the monomer, and solvent monomer interactions for each polymer. What is the alpha? So remember, our alpha is basically the ratio of our mean square displacement, r squared. Actually, let's go ahead and write it like this. Our mean square displacement of the polymer over our unperturbed state. So for each of these polymers, so for 1 and 3, alpha is greater than 1. For 1 and 2, alpha is actually for number 2, alpha, so this is for 1, 3, 1 comma 3. For number 2, alpha is less than 1, and for 4, alpha is equal to 1. So I know if alpha is greater than 1, my interactions of the monomer solvent interactions are basically very, very, very low, i.e. they are favorable interactions. So the polymer wants to expand, they want to maximize these monomer solvent interactions, and our monomer interactions are very unfavorable, they are high. Vice versa for monomer solvents here, when the polymer collapses, they're very high, kind of think of like a hydrophilic molecule in water, versus my monomer interactions, which are lower. So, and then for here, your monomer solvent interactions are 0, which are equal to your monomer. Anyways, so that's your unperturbed state. Rank the size and number of microstates. So the size for each of the for each polymer, again, for 1 and 3. So if I look at 1 and 3, they're kind of similar. So 1 and 3 will be the largest sizes. Then my next material will be number 4, and then the last material will be the one that collapses, which is number 2. And again, you could kind of describe that. You could get a little bit more detailed because remember, our mean square displacement is going to be equal to our kind of C infinity, our alpha squared, and then your kind of usual NL squared. But anyways, you could kind of rank those values, good solvent, bad solvent, and you could kind of read through the notes for those. How does each polymer size scale with N? So, or actually, my number of microstates. So actually, number 4 is the unperturbed, so my number of microstates, so number of microstates is the greatest for 4, which is greater than microstates for 1, 2, and 3. So this is the large number of microstates because whether I'm expanded or I'm collapsed, that's the scaling. So my mean square, so if I look at my mean square displacement, how does this scale with N? So for a good solvent or a theta solvent, or basically when my alpha is equal to 1, it's going to be a half. If it is my good solvent, my alpha is greater than 1, it's going to be the 3/5. And if it is my alpha, actually it's going to be a 2/3, excuse me. So 2/3. And then if I am less than 1, so if I'm in a bad solvent, it is going to be basically, my N is going to scale as, for a bad solvent, it's going to be 1/3. 1/3. So 2/3, exactly. So we can see again, looking at the scaling and the size, we get these different kind of values here. So there we go. So we've got our mean square displacement, all those scaling, and we got it. Rank the TG of the polymers. So I'm going to say between this one and this one, it's kind of hard. I've got 2 phenyl groups here. These methyl groups can be a problem, but I've got this bonding. So I'm going to say TG of 2 is greater than TG of 4, which is greater than TG now of 3, and then my lowest one is going to be my TG of 1. And you can justify that based on, again, very rigid here. We have H bonding here. The methyl groups, we have the steric interaction, maybe H bonding here. So these are going to be the 2 top candidates. Long side chain, methyl group, and here the rotations are quite easy. Look at the DSC curves below and label endo and exo. So again, whenever I'm looking at these curves, normally, from what we've seen previously, if I have a polymer, it's going to look like this. This indicates my TG. I need to absorb energy here, and we know that this is a melting transition possibly. So this is going to be my endo. This is going to be my XO. So when this slope goes down, I know that this is my endo, this is my XO, And now I can kind of look at, all right, well, this one has a low TG. Here's my TG here for this yellow one. Here's my, I don't have the TG actually for this orange one. Here's my TG for this guy. Here's the TG for this guy. And then here's the TG for this guy. So if I try to look and figure out, okay, which is my polymer, and then I have a mystery polymer too. So the last one, this is an exo. This curve here, this orange one, let's shift it. This orange one looks like this. This has an exo curve. I don't have any melting. I think that this is a thermoset polymer, so it's curing. It could have this could also be, again, a crystalline material, but I don't see the TG. But again, that might not be a good answer. So here I clearly see this is my highest TG. So I could say that this is going to be for my ranking, I said that this is TG2. So I could say that this is 2, 3, 2, or actually 2, 4, excuse me. 2, 4, 2, 4, 3, 3, 1, 2, 4, 3, 1. 2, 4, 3, 1. Is this correct? So if I'm looking at this curve here, let's trace it. I've got my TG, and then I've got my melting temperature. So is number 2 a semicrystalline? Yeah. So 1, 2, and 4 are semicrystalline. So here's my other one. I got this. This is my 1. So that's my number 1, and the TG is way over here. So 1 was my lowest. Okay, that makes sense. Semicrystalline. Let's look where number 4 is. 4, I got this. Another melting temperature. Fantastic. And then let's kind of erase what we've got here. Let's kind of see what we've got. So that could be a thermoset, or, oops, where's my other little polymer? So this guy right here. We kind of crossed over it. So this is my TG, and there's nothing else because it's amorphous. So we labeled those correctly. We got it, and then excellent. XRD plot, intensity versus 2 theta. If I'm doing polymer 1, I'm going to do that in red. So polymer 1 is semicrystalline, so I'm going to expect some sharp peaks. Polymer 3, I'm going to expect that, let's go back to my draw function here. I'm going to expect polymer 3 is going to be amorphous, so that might be more broad. That's it. That is question 2 in a nutshell. So remember those interactions, and then, yeah, we should be good to go. Excellent. I'll see you in the next video. Thanks for number 3. Bye.